Welcome to partial fraction decomposition. I have spent the better part of a year struggling with this topic. It's how to integrate rational expressions in a very specific manner. And yeah, I'm just gonna try to make a video on it. So let's see what happens. Okay, so imagine that we have an integral f of x over g of x, and we want to integrate with respect to x such that f and g specifically are both polynomials. So there's a polynomial in the numerator and there's a polynomial in the denominator. Knowing how to integrate such an expression basically upgrades our toolbox because now we can tackle integrals like this, and even like this, assuming that we do it correctly. And I I don't know that I can. I'll try. This is gonna be the hardest video I've ever made. Partial fraction decomposition is not an easy topic for me personally, but that's why I wanted to make a video on it. Let's look at some simpler integrals that could use partial fraction decomposition. Well, these are a lot simpler. For this one, this first one specifically, honestly, I'm pretty sure U substitution could work for this. Let's just see. So like, I'm pretty sure you could use U substitution for that. Or like for this one here, I think you can also use U substitution. I think that's the answer. Okay. So this one was right. So we could solve these two with U substitution. For some reason, Wolfram Alpha uses the log base 10 instead of natural logarithm. I don't know why. I have no idea why. But you know what? It's cool. All right. We're just grateful for the resource. This is correct. So is this. But I don't know about the last two. I don't know about the last two. I don't know if we could do the last two with U substitution. But the idea here is like first we'll see how to take the general rational function, then we'll do some algebra um to make it in a sum of simpler rational functions. And then we'll see how to integrate the simpler types of rational functions. And the simpler functions that are being referred to are all like these guys. They either have a constant over a linear power or they just look like a linear function over a quadratic. So we'll look at the algebra first and then we'll look at the calculus. So let's investigate the algebra of partial fractions. What we want to do is break up a rational function into simpler pieces. The first thing that we have to do is make sure that the numerator of the function has a degree that's less than the denominator. Because if it doesn't, then we have to start off the process by doing long division. So let's look at example 1 here. Okay, here the degree in the denominator is larger than the degree in the numerator, so this is fine. We're not gonna have to do a long division with this example 1. But with example 2, the degree in the numerator, the highest degree in the numerator is that of the same of the highest degree in the denominator. They're both raised to the degree of 2, which means that we're going to have to do some polynomial long division. Now note that we would have the same trouble if there was a cubic or a higher degree polynomial on the top, and we'd have to do long division. But even just with these degrees being the same, we need to do some long division. So long division is going to go like this. And so this is the numerator here is the dividend, I'm pretty sure, and then the denominator here is the divisor. So on the outside here, we're going to have x squared minus 1, and the inside will have our x raised to the fifth, excuse me, on the inside we'll have 5x raised to the second plus x minus 3. Okay, and so the first thing that we're going to do is we're going to divide the first terms. So we're going to, I think that the first thing we need to do is we're going to grab I was going to do this over here, 5x squared divided by x squared, and that equals 5. Okay, I'm pretty sure. And then that means that I put a 5 up top. And then I think that I multiply that 5 back to the the divisor. So then we'll do 5 times x squared minus 1. I get 5x squared minus 5. Okay. So then I have to subtract this here from the dividend, I'm pretty sure. And then you gotta like line it up right. Let me see here. 5x squared. There are no x's involved, so let me put some parentheses. So it's just gonna be plus 0 minus 5. And then like I have to like distribute this negative sign, I'm pretty sure. So upon distribution, this is actually gonna become positive 5, 0. It doesn't really matter because it's a 0. And so this is gonna be 0 plus x plus 2, which is the same thing as um x plus 2. And then so the division shows that we get a quotient of 5 with a remainder of x plus 2. I think it goes like this. Let's see. That means that we get stick an integral here, put a dx here. Okay. And then for this guy, I'm not even gonna put comma. For this one, I think it's like, oh, let's make it parenthetical. Dx. I think it goes like that. I'm pretty sure. And then now, because of the linearity rule, we can break up the integral into two pieces. The integral of 5 with respect to integration with respect to x plus the integral of x plus 2 x squared minus 1 integration with respect to x. First part, that's going to be 5x. We can just integrate 5 integration with respect to x, we get 5x. But with this guy, this second term is a little bit more tricky. The indefinite integral of x plus 2 over x squared minus 1 integration with respect to x. The new integral has a degree of 1 on the top and a degree of 2 on the bottom, is which is the way that it's supposed to be. And we can proceed further. So I think the move is to probably okay. So we'll factor the denominator, and then if the denominator is a quadratic, then we'll check the discriminant. And if this is negative, then you can't factor the quadratic. Otherwise, you can factor it by hand or just using the quadratic formula. Um, and then if the denominator is more complicated, then you might have to guess a root and do long division. But after factoring the denominator, the next step after that is to write something down called like what's the form. And then this is the part that like always tripped me up when it came to partial fraction decomposition. This next part is like the hard part in my opinion. Well, this is made by adding together one or more terms for each factor of the denominator. And let me show you guys the rules. All right, so here are the partial fraction decomposition rules of the form. Rule number 1 is that if you have a linear factor, x plus a, then the form has a term like capital A over x plus a. Rule number 2 is that if you have the square of a linear factor, x plus a quantity raised to the second power. Then the form has terms like capital A over x plus a quantity raised to the second power plus capital B over x plus a. Rule number 3 is that if you have a quadratic factor, x squared plus a times x plus b quantity, or just x squared plus a times x plus b, then the form has a term like capital A times x plus capital B over x squared plus a times x plus b. Now those are the most common ones, but here are some rare ones. That is rule number 4. If you have the cube of a linear factor x plus a quantity cubed, then the form has terms like capital A over x plus a quantity cubed plus capital B over x plus a quantity squared plus capital C over x plus a. Rule number 5 is that if you have the fourth power of a linear factor x plus a quantity raised to the fourth power, then the form has terms like capital A over x plus a quantity raised to the fourth power plus capital B over x plus a quantity raised to the third power plus capital C over x plus a quantity raised to the second power plus capital D over x plus a. Now notice that the form only depends on the denominator. The numerator is totally irrelevant. Um, Also notice that when naming the constants, we're using terms like A, B, C, D. Just keep in mind that you cannot reuse constants in different terms. So like you have to keep advancing along the alphabet. Unless you want to use one variable and start using subscripts for it, but if you do that, you're playing with fire. Um, so so yeah. All right, let's grab our example 1 that we didn't have to do any sort of long division on. Let's just grab that and we're just going to bring it over here and we're just going to see what's going on. But let's just like look at this denominator. X squared minus 1. Well, let me see here. Looks like there's a formula that we can apply to that. How does it go again? A plus B times A minus B. I think it was like that. So then that means that x squared minus 1, well, that means that this equals x plus 1 times x minus 1. And so then, interestingly enough, we have two linear factors. And then let's just see really quickly here. So we have two linear factors, and we have to keep advancing along the alphabet. So since the denominator has two linear factors, then the form is going to look like this. So that here, this would be the proper form. We found the form, and so let's just write down that the integrand equals that form, and then multiply it through by the denominator. We found that that form of the integrand is given by a over x minus 1 plus b over x plus 1. Um, let's see. And so then we can write, like, we could just like look at our integrand. We could say that x plus 2 over x squared minus 1 equals a over x minus 1 plus b over x plus 1. And honestly, I think we're better off writing the denominator on the left-hand side in the factored form. So we could write x plus 2, and then the denominator we'll put it in a factored form. X minus 1 x plus 1, difference of squares, right? Equals a over x minus 1 plus b over x plus 1. Um, and then we have to multiply both sides by the LCD. So yeah, let's just go. Let's play. Um, x minus 1, x plus 1. So then what's going to end up happening here is, well, it looks like obviously these are going to cancel with these. You know what? Let's use a different color. Let's use a different color. What color should we use? Oh, I don't know. How about blue? Let's do x minus, okay, so x minus 1, x plus 1 are going to cancel with these. Um, x minus 1 here is going to cancel with x minus 1 here. And then we'll use purple. Then x plus 1 is going to cancel with x plus 1. But this is still going to go to here. And, well, this is still going to go to here. Oops. And so I think what we're going to end up happening, I think, and then I think what's going to end up happening in the integrand is we're going to have x plus 2 equals, let's see, a gets multiplied to um, x plus 1, and then b gets multiplied to x minus 1. Okay, and then we'll do some distribution here. Say x plus 2 equals um, ax plus a plus bx minus b. I'm pretty sure. So just notice that the factor x minus 1 cancels with the first term on the right hand side, and then the factor x plus 1 cancels out with the second term. And there are two different ways that we could proceed. The first way is to substitute values of x. Like if you put um, x equals 1, then if you put like x equals 1, then b times x minus 1, like we don't, like, let's just not even think about, like, let's just look over here. Let's ignore this for now. I kind of went overboard. I shouldn't have proceeded further that much, but especially with this way of solving, because there's two different ways to solve it. If I substitute in x equals 1, then the b times x minus 1, that term just goes away, and then we would get, let's see. Oh wait, I should be clear for this whole thing here. If I set x equals 1, this equals 1, we would get 1 plus 2 equals um, a times 1 plus 1. Um, and then, what? Well, that's going to be 3 equals 2a. Then if I divide by 2, that will show us that a equals 3 over 2. Um, and then instead, right, if you put like, And that's that case. Let me see, and I'm gonna do a different color here. Like instead, if you put x equals -1, in the original equation, then we'll find that the a times x plus 1 term goes away. And then we're going to get, oh, let's see, -1 plus 2 equals b times -1 minus 1. Um, and then in such a case, it will show that equals b equals -1/2. But alternatively, there's another way to do things that, well, there's actually two other ways that we could do this. But let's talk about the second way before we get to the third, because I don't really like the third way, to be honest. Um, but it still works. But the second way is we could find a and b. So another way of like finding what a and b is to take the original equation. Okay, so this is our original equation. X plus 2 equals a times x plus 1 quantity plus b times x minus 1 quantity. And then we can go ahead and just rewrite this. Like x plus 2 equals a times x plus a plus b times x minus b. And I gotta like try to like group these things together. So x plus 2, it's just gonna stay the same. So this one comes from like factoring out. So if I factor out that x, which honestly I could switch it up. Wait. A plus b, because that that x can get factored out on the right side. Why not? Plus a minus b. All right, so this is what we're looking at here. So basically, this is what we're looking at. X plus 2 equals a plus b quantity times x plus a minus b quantity. Okay. Well, basically, we want to identify the coefficients of x on both sides. All right. So we're looking at this whole equation. I'm just going to rewrite it here because I don't know, something in my brain is telling me to rewrite it over here. I know that it's always I know that it's over there, and so technically I don't have to rewrite it out, but I don't know, guys. I just have this feeling that I need to do this. So, it looks a little bit more neater, and it's also bigger. So, um, so we have to identify the coefficients of x on both sides. The x terms on the left-hand side, well, this x over here, this is the same thing as x times 1. Rather, let's do this. Or 1 times x. That's 1 times x. And so the coefficient is 1. Um, let's see, on the right-hand side, there's an x here. And well, this is the coefficient right here. A plus b is the coefficient for this x. Um, and so we found the coefficients of x, right? That's the coefficient for x right there. And then um, let's see. Where are the constant terms? So where are the constant terms? So on the left side of the equation, 2 is the constant. That stands for constant. And then on the right hand side of the equation, this is the constant here because there's no x. All right. Um, so we have to set up the system of equations. So let's look at the terms that have a coefficient of x. The terms that have a coefficient of x, well, that's going to be a plus b, and this is going to equal 1. Right? Because because look, we're looking at the ones that have the coefficient of x, okay? And then coefficient of x right here on the right-hand side of the equation, that's going to be a plus b. But then on the left-hand side of the equation, we have x plus 2, and the coefficient in front of x is 1, so we'll set this equal to 1. Then we have to find the constant. So this will be constant. Const stands for constant. Um, and from the constant terms are right over here, and it's going to be a minus b, and we could write this out as a matrix C, but I don't want to make it too confusing, um, or do it wrong. We could try to write it out as a matrix C. Let's see if we have room. But first, let's just let's do this first, and then the constant on the left-hand side of the equation is 2. So yeah, let's write it over here as a matrix C. If we wanted to write this as a matrix C, we could do 1, 1, 1. What is this? A 2 by 3 matrix C. Then we would do over here 1, negative 1, 2. That's what the matrice would look like. But let's just keep going. So if we want to solve the system, and the easiest way to solve this specific system is by elimination, and that means elimination means to add the two equations together, because the plus b over here and this minus b over here, they'll cancel each other out. So let's add equations 1 and 2 together, and then this equals and then this equals 1 2 1 plus 2. Uh-oh. Hold on. My headset might be dying. 1 second. No, it's not. It's just randomly beeping. I hope I'm still being recorded. Okay, anyway. I'm like mid calculation here. Looks like these b's are gonna cancel. We'll get 2a. Well, 2a equals 3, and then we'll divide by 2 on this side, divide by 2 on that side, and that's going to reveal to us that a equals 3/2. And then yeah, guys. And so then let's see. We'll have to substitute a back into the original equation. So um we know what a is, you guys. We know what a is. So if we want to substitute it back into the original equation, that equation is going to be a plus b equals 1. So a plus b equals 1. So then if we substitute a back into the original equation because we know what a is, it's going to be 3 over 2 plus b equals 1. And then and if we move, let's see, I'm gonna do this back over here. It's crazy because I have all this room up here we could have utilized. Okay, anyway, I hope you guys can follow the logic. That this is, I mean, I know it doesn't look the prettiest, but it's okay, guys. 3 plus 2 plus b. Well, how about we move that 3/2 to the other side? We're gonna have b equals 1 minus 3/2. And then what is that? The same thing as b equals 2 over 2, a form of 1 minus 3 over 2 equals negative 1/2. So then what? B is negative 1/2. So that said, let's write out that um, a equals 3/2 and b equals negative 1/2. Okay. Then I think what we need to do, I'm pretty sure, is that we have to plug that back in up here. So like up here where we see this a plus b, excuse me, a over x minus 1 plus b over x plus 1. Then we plug back in the where a is. So like right here, we plug in 3/2, and then where b is, we plug in -1/2, I'm pretty sure. But before we do that, you guys might be thinking to yourself, okay, well, Stella, you said that you knew of a third way. Yes, I do know of a third way, guys. It's to use your calculator, but let's be honest, who wants to do that? I mean, I personally don't want to do that. I really feel like awful when I use my calculator for things like this. It just makes me feel like a failure. But if you want to use it, or like for an example, honestly, it makes me feel like a failure, yeah, but only like when I don't know how, like, or like what I'm doing exactly. And I told you guys, I was struggling for a bit with partial fraction decomposition, but they say walk before you run. So like, you learn your multiplication tables before you get a calculator to use it, for your multiplication tables. So that's the same sort of idea. So if you want to use this, if you want to use your TI-84 for this sort of thing, go ahead and hit apps on it. Then go down to where it says PLYSMLT2, and then it'll bring you to a main menu, and then there will be something that says simultaneous equation solver, and then well, from there it's pretty self-explanatory. You just can't change the variables. You're stuck with like x, y, and if it's a system of equations, if there's like a third variable, like if it's x squared, then x and then a constant for the system of equations, then you can introduce z, and you can use like matrices and stuff like that. But I'm not going to do a tutorial on how to do that because I honestly don't really want to right now. So I want to do the actual math. Um, Now, but if that's how you could use your calculator to find it if you want. Um, let's let's keep this going, guys. Let's keep this going. I think so. We have our A, we have our B. Did I even find the B from? Oh yeah, I did. Okay, let's let's go ahead and let's solve this. So here are two ways that you can mathematically solve for A and B without using a calculator. And now for the sake of more room, we'll use this over here. All I did was I brought over our integral, the original integral. I brought up the partial fraction decomposition, this here, and then I brought our A and B values, which we found down here and over here. All right, so we're just gonna keep working through this. So all that's left to do at this point is to rewrite the integrand as equal to the form. Um, but this time we can have our A and B constants filled in, right? So we'll bring these over in the numerator over here. We're going to have 3/2. And then in the numerator over here, we're going to have a -1/2. And this is going to be 3/2 is going to represent A, because that's what A is. So 3/2 over x minus 1 plus -1/2 over x plus 1. Okay? And now we're going to integrate both sides. So, oh, excuse me. Now we're going to integrate both terms. So let me just rewrite this, right? So we're going to have the integral of x plus 2 over x squared minus 1, integration with respect to x, equals, and we're going to apply the integral to both of these because of the linearity rule for integration, equals 3/2 over x minus 1 plus, all right, I guess, yeah, we could do, yeah, okay, just to not be confused. So plus the integral of -1/2 over x plus 1. Oh, shoot, I forgot to put my integration with respect to x over here. And let me just move this over. and then integration with respect to x over here. And then now, I think the move is to probably factor out. Remember, 3/2 and -1/2 are constant, so we're just gonna factor those out of the integrals. So we'll have 3/2 um times 1 over x minus 1 integration with respect to x, and then factor out that -1/2, and so that positive sign turns into a subtraction um sign. So you get 1/2 times the integral of 1 over x plus 1 integration with respect to x. Now, mm, let us work away on 3 over 2 times, no, yeah, times the integral of 1 over x minus 1 integration with respect to x. And we're going to leave this one alone for a second here because if we did some u substitution and we set, well, let's set u to um, x minus 1. What's the derivative of x minus 1? Derivative of x is 1. The derivative of -1 is 0. So du is going to be just equal to dx. And then we could substitute that. Uh, let's see, bring it back over here. So 3 over 2 times, yeah, times the integral of 1 over u. Well, yeah, du. And then we can write out one of our rules here. It goes like the integral of 1 over x integration with respect to x equals, how does it go? The natural logarithm of x plus c. I think that's how it goes, right? Pretty sure. Pretty sure, pretty sure. So we're gonna hit it with that. Um, so then what we're gonna end up with is see here, 3/2 times the natural log of u plus c. Um, and then we have to back substitute, which basically means that I'm just gonna put back the u that we set u to. So we had set u to x minus 1, so this is gonna be 3/2 times the natural logarithm of x minus 1 plus c. And so that's gonna be the first integral. Uh, the second integral, yeah, yeah, second integral. The second integral is 1/2 of the one half times the integral of 1 over x plus 1 integration with respect to x, and I'm pretty sure that we can also do a substitution. Substitution. Um, and so where u equals what? X plus 1. All right, and then the derivative of x equals 1. The derivative of 1 is 0, so we're going to have dx right here. All right, then we're going to have negative 1/2 times the integral of x plus, wait. No, because we're substituting. What am I doing? 1 over u, integration with respect to u. And we're going to hit it with this same formula here. The same formula here, because it's going to go like, well, it's going to be negative 1/2 times the natural logarithm of the absolute value of u plus c. And we have to back substitute. So we'll back substitute negative 1/2 times the natural logarithm of x plus 1. Oops. X plus 1 plus c. And so I think it goes like this. Here, this is the arbitrary constant. This is the first arbitrary constant. This is the second arbitrary constant. But then we're gonna like combine them, so they're gonna be like a third arbitrary constant. But then we could just write that as like, okay, like c plus 1 plus c plus 2 equals c plus 3. But we could also just write that as c. It's just an arbitrary constant. So I'm saying this because we're gonna combine our two answers here. So we're gonna have 3 over 2 times the natural logarithm of the absolute value of x minus 1 minus, and I'm just going to tag the third arbitrary constant on the end, and I'm just going to call it c, minus 1/2 times the natural logarithm of the absolute value of x plus 1 plus c. And so that's going to be our answer. I'm pretty sure. Should we check? Let's check. Yeah, we got it. I don't know why. If anybody knows why they put log base 10 instead of the natural logarithm, please tell me. Because they don't mean the same thing. But I know that this is the answer because I know that this is the rule. Let's do another example. So here we have the indefinite integral of 1 over 4 times x minus 5 integration with respect to x. Well, here we can solve this with u substitution. So let's let u equal 4x minus 5. And the derivative of 4x minus 5, well, first we'll do the derivative of 4x, and we'll factor out that 4 really quickly, and then we'll take the derivative of x, which is 1, then we'll multiply back that 4. So the derivative of 4x is 4. All right, and then 5, the derivative of 5 is going to be 0, so we'll have 4 minus 0, which of course is just going to be 4 dx. But the issue here is there's no 4 dx. There's 4 times x minus 5 quantity, but there's no just 4x. So we'll have to divide both sides here and here by 4, and that's going to give us 1/4 du equals dx. And now the substitution should go a little bit more smoothly. That is, now the substitution is allowed. So we'll go ahead with the substitution, and we'll do, so let's see, 4x minus 5. So 1 over 4x minus 5 integration with respect to x. Well, that's going to become the indefinite integral of 1 over u times 1/4 du. And of course, we could just factor out that 1/4 from the integrand, the 1 over 4 from the integrand. So we got 1/4 times the indefinite integral of 1 over u integration with respect to u. And now the thing about this one is there's a formula that we could use to solve this. The same formula from before. It's going to be, well, the integral of 1 over x integration with respect to x equals the natural logarithm of the absolute value of x plus c. All right. And so we'll apply this rule here, and we'll have 1 over 4 times the natural logarithm of the absolute value of u plus c. And then we'll have to back substitute. And so what that will look like is 1/4 natural logarithm of what we set u2, which is going to be the absolute value of 4 times x minus 5 plus c. And that will be our answer. All right. Now, the same trick works for a power of a linear factor in the denominator. So like for an example, right? If we have that exact same thing, right? And I'm just copying this from up here, except I'm going to square the entire thing in the bottom. That is 1 over, oh, with that. That is the indefinite integral of 1 over 4x minus 5 quantity squared integration with respect to x. But we can do the exact same thing, right? We're just going to substitute. All right, let u equal 4x minus 5, um, and du, its derivative, it will be 4. And then just like from before, we're going to divide both sides by 4. We're going to have 1/4 du equals dx. Oh, yeah, let me just go ahead and write in our dx. So now what we'll do is we'll just apply our substitution. And we're going to have 1 over u squared times 1/4 du. And then just like before, we're just going to factor out that 1/4. And then what I think I'm going to actually bring that u upstairs. So now we'll have u raised to the negative second power integration with respect to u. This will be a classic power rule situation. That is, if you have x raised to the power of n, the integral of x raised to the power of n, integration with respect to x, that's going to equal x raised to the power of n plus 1, and the denominator will have, it's all going to be over n plus 1. All right, so we'll apply that. So we're going to have 1 over 4, and then this is going to be times, oh gosh, almost forgot, plus c, right? This is going to be 1 over 4 times, well, we'll see, it's going to be b raised to the negative second plus 1, and the denominator is going to be negative 2 plus 1, plus c. This is going to be, this is going to be 1 over 4 times negative u raised to the negative first power plus c. And I'm going to put that u in the denominator here, so we're going to have 1/4 times negative 1 over u plus c, and then we're going to hit it with that back substitution. So right, back sub, So the back substitution is going to be like, we're going to have 1 over 4 times negative 4x, well, negative 1 over 4x minus 5 plus c here. And so here, then this is going to be, well, let me do that bottom there first. So we'll do, well, can't forget that negative. Um, well, negative 1 over 4 times 4x minus 5 quantity plus c. And let's see, we could simplify that out further if we'd like to. The 16x minus 20 in the denominator there, and then a negative 1 up top plus c. All right, so these are two different representations of our answer here. Okay, but where it starts to become a little bit more difficult is when we have a quadratic in the denominator. So if we have like a quadratic in the denominator, and that's going to be like the indefinite integral from of a times capital A times x plus b over a lowercase a times x raised to the second power plus lowercase b times x plus c integration with respect to x. All right. That's a little bit more difficult. And if the quadratic can be factored, well, then we need to do that first. And that was the case with our last problem. Let's see if I can find it over here, right? Where we had to factor that difference of squares in the denominator, and we had to write it as x minus 1 quantity times x plus 1 quantity, and that eventually led to two integrals whose integrands had linear denominators, so there was no need to integrate anything with a quadratic on the bottom. Now, even the previous example that we had just done, let's see here, with the 4x, with the denominator of 4x minus 5 quantity squared on the bottom, that didn't pose a problem since we just had to deal with the square of the linear term. So what's left? Well, the only possibility is that the quadratic on the bottom cannot be factored. That is, its discriminant, b squared minus 4 times a times c, is negative. So an example of like an integral like this, it would be like, it would, let's see, it would look like this. Right? If we have the indefinite integral of x plus 8 over x squared plus 6x plus 13 integration with respect to x, that the denominator, well, it's quadratic, and so it's a quadratic. The quadratic, it's of the form a times x squared plus bx plus c. Okay, and then the discriminant, the discriminant, it's like, let's see, it's like four, no, b squared minus 4ac, um, and and so let's check to see if the discriminant here if it's negative. All right. So so in our case, let's see here. Honestly, I don't need that arrow. So in our case, let's see, we have our case we have x squared. Well, hold on. In our case, we have 1x squared plus 6x plus 13. All right, such that a equals 1, um, b equals 6, c equals 13. And so let's go ahead and find our discriminant here. So we're going to actually have, let's see, 6 raised to the second times 4 times 1 times 13. And so 13 and 13 is 26. 26 plus 26 is going to be, yeah, I think it's going to be 52. So 52 here. This is going to be 36. Let's see, 36 minus 52. The denominator is discriminant. It's negative, and we don't have to do any of the algebra that we did previously in this case, since the denominator can't be factored. There's no need to use any form at all. We just have to do the integral. And so here's how. In order to do the integral with this case here, we have to complete the square. So let's complete the square in our example. And honestly, I'm gonna just move this over to a fresh page. Yeah. All right. So let's just do a quick recap, right? We got this integral here, the indefinite integral of x plus 8 over x squared plus 6x plus 13, integration with respect to x. And because the denominator here is quadratic, we checked its discriminant, which was negative. And because the discriminant is negative, well, we know that the denominator cannot be factored, at least in the real numbers. I think it'll go into complex numbers, imaginary numbers, um and so what we're gonna do with this is, well, we're going to complete the square. So just quickly, we checked the discriminant for x squared plus 6x plus 13, and we checked this discriminant. We found that the discriminant was negative, which means that that it's not factorable. This quadratic here, it's not factorable in the real numbers. And so what's the move? The move is to complete the square. So when it comes to completing the square, um, the first thing that we have to do is we have to isolate like the x terms mentally. So I mean, what are we looking at here? We're looking at x squared plus 6x plus 13. All right. So let's just turn our attention to this x squared plus 6x. And we're only going to focus on this x squared plus 6x. And well, for this portion here, we could say that we could write a formula. We could write a formula that so if it is of the form x squared plus bx, and here 6x, it represents bx, so 6 is b, Um, then, to complete the square, we take the coefficient of x, which is b, we half it, we square it, and then we subtract and add that number. So to find the number that we want, it says number we want, we are going to, the number that we want is equal to um, b over 2. For us, we're going to take b, um, so so b is equal to 6, and then uh, so that means that we're going to take b, we're going to take 6, and then we're going to half it, which so we're going to get 3, and then we're going to raise to the power of 2, and then 3 raised to the power of 2 is 9. Um, and so then what we're going to do is we're going to add and subtract this 9 to our expression. So let's see, how does this go? It goes like this, I think. X squared plus 6x plus plus 9 minus 9, and then plus that 13 as well. And then we can simplify. Let's see. 13 plus 9, well, 13 minus 9 is going to be 4. So what is it? Negative? No, positive 4, right? So we'll have x squared plus 6x plus 9, and we're going to just combine these guys here. So plus positive 4. I think, I'm not sure. I'm not 100%, honestly, but yeah, I think. And then I think the next thing to do is to recognize that this is a trinomial of the form, well, a squared plus 2ab. So this is of the form, well, a plus b quantity squared equals a squared plus 2ab plus b squared, I think. Well, if we have x squared plus 6x plus 9, just ignoring that 4 for now, well, that equals x plus 3 squared. Then we'll bring down that 9. No, excuse me, then we'll bring down that 4, and this is going to be x plus 3 raised to the second plus 4. And I think that's how you would complete the square on that. We've got our original integral, which was x plus 8 over x squared plus 6x plus 13. Integration with respect to x, and now that's the same thing as because we could rewrite it with the new denominator, which is which is um x plus 3 quantity raised to the second power plus 4. Oh, and then this is going to be, and the numerator, nope, and the numerator is going to be x plus 8. Integration with respect to x. I'm going to be honest with you guys, I'm kind of stuck. I have to try. So, well, let's say that um, let's say that we set u equal to x plus 3. Let's say that we wanted to solve this for x. X equals u minus 3. But then we want to take the derivative of u. So we get du equals 1 dx. So then like we could like rewrite our integral, right? Well, now we've got in the denominator u squared plus 4. We're in the numerator. We solve for x in the numerator. So that's going to be well, u minus 3. This is plus 8 integration with respect to x. And then let's just simplify this. But if we remove those parentheses, that's going to be u plus 5. And then in the denominator, it's going to be u squared plus 4. Oops, I just realized something. This is not integration with respect to x. We just switched variables and applied a substitution. So this is integration with respect to u, as it is over here. And now it's like the next step is to, I think we have to break this integral. Wait, oh yeah, we can break this integral. We can break this integral into two integrals, I think, right? Yeah, I'm pretty sure we can, guys, because and we could split this fraction here. And so, let's see, the indefinite integral of u squared, the indefinite integral of u squared plus 4 in the denominator. So we got the indefinite integral of u over u squared plus 4 plus the indefinite integral of, well, the denominator is going to stay the same, u squared plus 4 in the denominator, and then up top we'll have a 5. Um, but we can pull that 5 out front. So we'll have the indefinite integral of u over u squared plus 4. Oh my gosh, what am I doing, you guys? I keep forgetting to write in the du. Honestly, I have no excuse. I have no excuse. Let's just get it in there and keep going. Let's see, u over u squared plus 4 integration with respect to u plus 5, because we're going to factor that out, times the integral of 1 over u squared plus 4 integration with respect to u. You guys, I'm stuck. It's time for me to grab my textbook and read. Let me try to figure out what's going on here. All right, so I read from my textbook. It's a book by Adrian Banner. Really good calculus textbook, by the way. Definitely recommend. Um, but he shows me this like mathematical trick shot in it. So basically, um, we look at the top and the bottom of this integral, and well, so we notice that um the top is a multiple of the derivative of the bottom, right? So let me just write out a rule for differentiation really quickly. Okay, so basically the derivative of the denominator, right? Like if I took the derivative of u squared plus 4, it would have me apply the power rule to that first term in the in what we're taking the derivative of the binomial of. And so it's going to become 2u and then, well, plus 0 because the derivative of 4 is 0. So this is like a mathematical trick shot. This is actually really cool. All right, so watch this, right? Because, well, his claim is that if you have a um you know if the derivative of the denominator and the numerator is a constant multiple of what his claim is that if the top is a multiple of the derivative of the bottom, which it is in this case because the derivative of this is, and I just get rid of this plus 0 just to get rid of the confusion, it's 2u. Well, u is a multiple of 2u, and so um his claim is that his claim is that we can multiply and divide the integrand by 2. So, oops, 2 over 2, which it's a form of 1, interestingly enough. Okay, so maybe this will work. I'm not sure. Let's try to see what's going on here. Let's just work it through. Um, so 2 over 2 times our integrand, which is u times, excuse me, u over u squared plus 4 integration with respect to u. So that's going to look like, well, 2u in the numerator, and then 2 times u squared plus 4. But integration with respect to u, but I would guess what would have to be done in this context is that we would have to factor out 1/2. I think we would have to factor out 1/2. This is really weird. I've never seen anything like this before. Let's hope this works, guys. If this works, this is like a real mathematical trick shot. I mean, this is something that is just, if this works, well, let's hold on. I'm excited. Let's just see what happens. U squared plus 4, and that's going to go underneath 2u. We're going to have to try to u substitute this, guys. We're going to have to try to u substitute this. Oh, yeah, and for clarity, this is the same, working on this integral right now. This integral right now. This integral right now. This integral right now. We'll come back to this one in a second. So, this is going to be 1/2 times the integral of, let's see, 2u in the numerator, and u squared plus 4. And that's, well, integration with respect to u. What should we use, guys? What's a variable we should use? Phi. We'll let phi equal um, u squared plus 4. Because this is another round of u substitution. So we'll let the derivative of phi equal 2u. Dude, this might work. Hold on. Wait, I'm like really intrigued right now. I'm like really into this, you guys. 1/2 times. Oh, yeah, wait. That's supposed to be like that, du. That's the same thing as 1/2 times the integral of 1 over phi, integration with respect to phi. Oh my gosh, dude, this might actually work. Hold on, let me write out our logarithm rule. So that's going to mean that this is going to be 1/2 the natural logarithm, the absolute value of phi plus c, and that this is going to equal 1/2 the natural times the natural logarithm of what we set phi to. We're going to hit it with a back substitution. U squared plus 4 plus c. All right. just note that phi is a placeholder variable. And I do believe that u squared, anything that's squared is positive. So this is always going to be positive. So this is going to be 1/2 natural logarithm. We could just drop the absolute value signs, right? Or the absolute, yeah. So we could just put it, if we want to make it like parenthetical, just do u squared plus 4 plus c. Oh, so that's the answer to that. This is the answer to that integral. But we still have to, well, I think, I don't know. We won't know until the very end because I'm gonna Wolfram Alpha this at the end, because I've never seen anything like this before. I've never learned. I didn't know. I mean, it would make sense intuitively speaking. I mean, you're just multiplying it by a form of one, but you kind of have like one part of the form of one hanging out outside the integral, and then the other one is like not, and then you did like, if this works though, this is like probably this is one of like the most clever things I've ever seen in mathematics. I mean, that's just if it works, I don't know that it works. So let's just keep going. Let's just keep going with this next integral. Um, I need more room. I undoubtedly need more room. So 1 second. All right. I don't even want to go to a new page, honestly, because I think that especially with the original u substitution, we're gonna need some of that. We gotta focus on this other integral. Let's do blue. This integral here, including the 5 that we factored out. So I don't know how we're gonna do this, guys. Let's see. Let's see. 5 times the indefinite integral of u squared plus 4. So 1 over u squared plus 4. Integration with respect to u. This might be trigonometric. So the formula will go like this. And so this says that if we have the indefinite integral of 1 over u squared plus a squared integration with respect to u, that equals 1 over a times arctangent of u over a plus c. And this is directly applicable to us because we have 5 times, let's see, 5 times 1 over u squared plus 2 raised to the second power. Um, Integration with respect to u, and that equals 1 over, wait, no, that doesn't equal 1, that equals 5 over 2 because we're going to multiply back that 5. So 5 halves um, times arctangent of, let's see, u over 2 plus c. I'm pretty sure. This here in dark blue is the same thing as this here in dark blue. This is the same thing. This is our answer, and we have to like connect them to each other. So that said, let's go ahead and do that. That's gonna be 1/2 natural logarithm of u squared plus 4 plus the first arbitrary constant um plus 5 halves times arctangent of u over 2 plus our second arbitrary constant. Um, One that's going to just become a third arbitrary constant. So we're going to have 1/2 times the natural logarithm of u squared plus 4 plus 5 over 2 arctangent of u over 2 plus, this is really c subscript 3, c to sub 3, but we're just going to leave it as c. Well, we have to replace u with x plus 3. So everywhere that we see u, we have to replace it with x plus 3. So we're going to back substitute. So we're going to have 1/2 natural logarithm of, well, this is u squared, but we're going to replace that with x plus 3 squared, because that's what we set u to, plus 4. And then we're going to do plus 5 over 2, 5/2, arctangent over the u over, so really x plus 3 over 2 plus c. X plus 3 squared plus 4. This is where we complete the square. X plus 3 squared plus 4, which x squared plus 6x plus 3. So this is the exact same thing. This is going to simplify, this is what we have on the page over here. X plus 3 quantity squared plus 4, x plus 3 quantity squared plus 4, which we got when we completed the square for the trinomial x squared plus 6x plus 13. So that's just going to immediately simplify back. Yeah, that's just gonna immediately simplify back. How can it not? So 1/2 times the natural logarithm of um see x squared plus 6x plus 13 plus 13 plus 5/2 times arctangent of um x plus 3 over 2 and plus our arbitrary constant. The indefinite integral of x plus 8 over x squared plus 6x plus 13 integration with respect to x is 1/2 times the natural logarithm of x squared plus 6x plus 13 plus 5/2 times arctangent of x plus 3 over 2 plus arbitrary constant. All right, guys. Let's uh let's use Wolfram Alpha to check our work. This is the moment of truth. We're gonna plug this into Wolfram Alpha, and just bear in mind that it uses log base 10 to describe natural logarithm for some odd reason. Interesting. So this is the same thing. This is the exact same thing. I think it just went about it a different way. But it is 1/2 times the logarithm, the natural logarithm of x squared plus 6x plus 13 plus 5. This is where we put our 5/2, which this would go to, this would get distributed to this would get distributed to this, of arctangent of 5 times arctangent of x plus 3 over 2 plus the constant. So yeah, we got it right. We did it. One thing that I want to go over really quickly before we move on. See, we just evaluated the indefinite integral of x plus 8 over x squared plus 6x plus 13 integration with respect to x. But one thing that we should go over before we move on is that if the original quadratic on the bottom isn't monic, meaning a monic means a polynomial where the leading coefficient is the number, the number attached to the variable with the highest exponent is exactly 1. In the situation where if the original quadratic on the bottom isn't monic, it's often good to pull out the leading coefficient before completing the square. So for an example, right? If we have an integral that looks like this, the integral of x plus 8 over 2 times x squared plus 12x plus 26, um, the move here would be to pull out a factor of 2 on the bottom, and then we could rewrite the integral. So we will just take out that 2 on the bottom. So we'll take out 1/2. And then the integrand on in the denominator, the polynomial, it will change and it will look like this. The numerator is going to stay the same. And so this is the same exact integral as before, except for the factor of 1/2 out front. So it's gonna simplify, and it's gonna look a lot like what we had before. What did we have before? So before, in the case of the indefinite integral of x plus 8 over x squared plus 6x plus 13, well, we found our answer to be 1/2 times the natural logarithm of x squared plus 6x plus 13 plus 5/2 times arctangent of x plus 3 over 2 plus the arbitrary constant. But in this case, where we have 1/2 times the the indefinite integral of x plus 8 over x squared plus 6x plus 13, which again came from the indefinite integral of x plus 8 over 2 times x squared plus 12x plus 26. We just factored out the 2 from the denominator. It's going to look a lot like what we had originally gotten, only um, only it's going to interact with the 1/2 that we factored out, so it should look like this. Right? So the only difference really is that is the 1/4 out front instead of a 1/2 out front. And also the um 5, it's not 5/2 anymore, it's 5/4 in front of arctangent. So I think next thing to do is probably to try to summarize the whole partial fraction method, and then we could work through another example. All right, so how do we find the integral of a rational function? Let's come up with a game plan for this. So the first step is to check the degrees and then divide if necessary. So you check to see if the degree of the numerator is less than the degree of the denominator, and if it is, then you're good. But if not, then you're going to do a long division and then proceed to the next step, which is going to be step 2. Step 2 is going to be to factor the denominator. You can use the quadratic formula, or you could try to guess the roots and divide to factor the denominator of the integrand. Step 3 is we gotta check, and you gotta check out the form. And then remember how how we went over the form previously. And so here's a quick refresher on how to check for the form. And chances are it's probably only going to be the first 3, but it could be the 4th and the 5th. So yeah, you write down the form with the undetermined constants, and then write down an equation like let's see, you write the integrand, and then next to it you write the form. And then the fourth thing to do is to evaluate the constants. So then step 4 is to evaluate the constants. Multiply both sides of the equation by the denominator, and then which is the lowest common denominator, and then find the constants by, you could either substitute like a value in for x, or you could try to equate the coefficients, or some combination of them both, or you could also use your calculator. Um, and then you can express your integral as the sum of rational functions which either have which either have constants on the top and powers of linear functions on the bottom, or it 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 might look like a linear function divided by a quadratic function. Um, and so then, so for step 5, that's going to be to integrate terms with linear powers at the bottom or on the bottom. So that is solve any integrals whose denominators are powers of linear functions, and the answer will involve logarithms or negative powers of the linear term. Step 6 is going to be to integrate the terms with quadratics on the bottom. That is for each integral with a non-factorable quadratic term in the denominator, complete the square, make a change of variables, and then possibly split up it into 2 integrals. The first one will involve logarithms, and the second one should involve arctangent. And if there's only one integral, it could involve either logarithms or uh, or arctangent. And a formula that's extremely useful most of the time is as follows. The definite integral of 1 over x squared plus a squared integration with respect to x equals 1 over a times arctangent of x over a plus the arbitrary constant. And remember that you don't always need to do all 6 steps. You don't have to always use all 6 steps. Sometimes you can go directly to the last step, like in the example that we just did, the indefinite integral of x plus 8 over x squared plus 6x plus 13 integration with respect to x, and that's from what we did previously. Let's do a really difficult one. All right, guys, so we have the indefinite integral of x raised to the fifth power minus 7 times x raised to the fourth power plus 19 times x raised to the third power minus 10 times x raised to the second power minus 19 times x plus 18 over x raised to the fourth power minus 5 times x raised to the third power plus 9 times x squared. Integration with respect to x. Now, I don't know if I could do this, to be honest with you, but the book challenges me to, so I think I'm going to try. Guys, YOLO. So I guess step 1 would be to check the degrees and divide if necessary. Now, obviously, when you look at this, and because of what I said before, this is going to involve all of the steps. So the first thing is to check the degrees, and we can see that the highest degree in the numerator is larger than the highest degree in the denominator. So yeah, guys, we're going to have to do some long division. I think the first thing that I need to do is I need to divide the first terms. So I'm going to grab x raised to the fifth, and I'm going to divide that by x raised to the fourth. That's just going to be x. And I'm going to take that x, and I'm going to put it up here. Okay. Then I think I have to multiply x to this entire thing, to this trinomial, I think. Right? Okay. Well, that's going to be x raised to the fifth minus 5x raised to the fourth plus 9x raised to the third, I'm pretty sure. And then I think we're gonna have to subtract. We have to line it up though. So what is this? X raised to the fifth minus x raised to the fifth minus 5x raised to the fourth plus 9x raised to the third. And then like we have to like distribute this, right? So distribute. Well, this is going to be x plus x raised to the fifth plus 5x raised to the fourth minus 9x raised to the third, right? And then I'm just gonna get rid of that. Wait a second. Yeah, we just get rid of that. So really, honestly, negative x. So that'll 0 plus, what is that? 2x raised to the fourth, negative 2x raised to the fourth, um, plus 10x plus 10x raised to the third, then what? Minus 10x raised to the second minus 19x plus 18x, right? And then what's the next highest term? It's like negative 2x raised to the fourth. Negative 2x raised to the fourth divided by x raised to the fourth. It's going to be 2. No, it's going to be negative 2. So then we'll put like a negative 2 up top. And then we have to multiply the negative 2. Negative 2 times x raised to the fourth minus 5 times x raised to the third plus 9 times x raised to the second. And then, well, that's going to be negative 2 times x raised to the fourth plus 10 times x raised to the third plus, no, minus 18 times x squared. Subtract. So they subtract the 2x raised to the fourth plus and 10x raised to the third minus 18x raised to the second. And then we're going to distribute that. So this is going to end up zeroing, pretty sure. Plus, oh no, that's going to end up zeroing too. And so it would be, I guess, plus 0. And this is going to be plus 18, so this is going to be plus 8x squared minus 19x plus 18. So we got x squared minus 19x plus 18. 8x squared minus 19x plus 18. And that's our remainder. I don't want this to be confusing, so I'm going to just move this over here. And that's the remainder. I think it's going to be like x minus 2 plus our remainder here. So x, no, 8 times x squared minus 19 times x plus 18 over the divisor here, 4 x raised to the power 4 minus 5x raised to the power 3 plus 9x squared. Should throw some parentheses on this. Integration with respect to x. So I think that's what it's going to look like now. The first two terms on the right-hand integral are, well, they integrate to well, let's see. Guys, this one's going to be like well, this one's going to be integral of x with respect to x. Oh, well, and then so for this one here, I'll work along this vertically, just because for some reason that's what makes sense in my brain. But this is going to be a power rule situation. So this is going to be like, well, integral of x with respect to x equals x raised to the second over 2, which is the same thing as 1/2 x squared. Well, the integral of 2x, integration with respect to x, the first thing to do is to just factor out that 2. And it's a negative, there's a negative sign, so it's -2. On the inside, there's just going to be a 1. And so that's just going to become, well, that's going to be -2x plus c, but we're going to ignore the plus c right now. So it'll be 1/2 times x squared minus 2x. And like I said, we're just going to add that plus c at the end. So we have to move on to step 2, which is factor the denominator. So we need to factor that denominator. Okay. All right, we can, we will, we shall. So we have a quartic. This is raised to the power of 4. We have a quartic in the denominator. But it has an obvious factor of x squared. So we'll go ahead and we'll factor that denominator. Yeah, we'll just factor it. So it's going to be like x raised to the 4th minus 5x raised to the 3rd plus 9x squared. They all have a factor of x squared in it. So if we just take out that x squared, well, it's going to become x squared minus 5x plus 9. We should probably check the discriminant for the quadratic. So let's just go ahead and check the discriminant. We can do that in purple. B squared minus 4ac. And so then for us, it's going to be, well, B is going to be -5, right? So we need, because I'm pretty sure the sign comes with it, so -5 squared minus 4 times A, which is just 1, and C, which is 9. Well, 5 times 5 is 25, minus, what is 9 times, is this 36? 36. So 9 times 4 is 36. Oh, yeah, guys, it's going to be negative. Let's see. What is that? -11? The discriminant is -11, and because this is negative, the quadratic can't be factored. So we're done with step 2. Let's just really quickly check step 3. The form, and here are our forms. We have 2 factors. We have x squared, and we have x squared minus 5 times x plus 9. And so we're not supposed to think of the first factor, x squared, as a quadratic, but instead we're supposed to think of it as a square of a linear factor. And so x squared, it's a square, so we can rewrite it as x minus 0 squared, I think. Which honestly helps us see it better. Okay. So then the factor x squared is going to contribute to the form. So let me just look really quickly here. Yeah. Oh, yeah, because look, guys, we have a square of a linear factor, x plus a squared, and that's for us x plus 0 squared. Then the form has terms like, oh, yo, guys, it's starting to make sense to me now. I hope it's starting to make sense to you guys. So I put some stars next to what we're going to be working with, because we do have a square of a linear factor, x plus 0 squared. I'm also gonna link the book that I'm referencing in this video so you guys can learn from it too, because it's pretty cool. And then we also have a quadratic um, of this exact form here. Um, so at this point, um, well, I'm just gonna rewrite this up here because I do want to utilize that space down there. But I do think that this is important to keep around because this actually makes a lot of sense. Um, yeah, yeah. So, well, the thing is, the x squared factor is going to contribute, and remember that the form for this x squared factor, well, and we could look at it here, um, for this x squared factor, um, so it's a linear factor. We have a square of a linear factor, namely, x minus 0 squared. So that means that it's going to have this type of form, x plus a squared plus b uh, plus a, and but also because it's a, yeah. So this is what it's going to look like. It's going to look like this is for x squared, by the way. This is for x squared. But it's going to be like a over x, no, x, no, a over x plus a over x plus 0 quantity squared plus b over x plus 0. Well, that's just going to be um x squared plus b over x. And then well, on the other hand, we have x squared minus 5 times x plus 9, right? X squared minus 5x um plus 9. And then if we look back here, we can see that, well, that's a quadratic factor, and it's going to have the following term: a times x plus b over x squared plus a times x plus b. Um, d, or c times x times, excuse me, c times x plus d. Sorry, I was thinking about something else. C times x plus d on top, and then on the bottom, x squared minus 5x plus 9. And then we're gonna have to like put these guys together. Well, this is gonna be a over x squared plus b over x plus c times x plus d over the quadratic, x squared minus 5x plus 9. Um, and we'll unpack that. We'll get to that. I just want to really quickly like recognize that this is going to be part of our answer, but this requires partial fractions, partial fraction decomposition. Um, so let's play. Well, the next step at this point is to evaluate the constants. Um, and so we have to evaluate the constants. So let's yeah, I think I'm gonna have to open up a new page for this. We don't have any more room. So we're making the jump from here to here. Just got our bearing straight. This says that 8 times x squared minus 19x plus 18 over x squared times x squared minus 5x plus 9 quantity equals a over x squared plus b over x plus c times x plus d over x squared minus 5 times x plus 9. And we're just gonna move on to step 4. So step 4 is to evaluate the constants, right? Um, so we have to find like what are the values for A, B, C, and D. And so the first thing that we need to do is multiply the entire thing by its LCD. Um, so we're gonna multiply the entire thing, both sides, right side and left side, by x squared times x squared minus 5 times x plus 9 quantity. So what I'll do here, I'm gonna stick this in parentheses, and I'm gonna stick this entire thing in parentheses. All right, this is gonna get multiplied to this side. Oops, this thing's gonna get multiplied. This thing's gonna get multiplied to this side, and it's gonna get multiplied to this side. And we're gonna have some cancellations, which is R, and it's well, it's this is what it's gonna turn into. As you can imagine, this is just gonna cancel the entirety of this. So on the left-hand side of the equation, we're gonna have 8 times x squared minus 19 times x plus 18. And then this x squared is going to cancel out with this x squared over here on the right-hand side of the equation. So a is going to equal a times x squared minus 5 times x plus 9 quantity. All right. Then we're going to multiply the lowest common, excuse me, the least common denominator to the second term on the right hand side of the equation, b over x, and then this x is going to cancel with this x, but there's still going to be one x left. So we're going to have plus b times x. So yeah, b times x uh, times um, x squared minus 5 times x plus 9 quantity. X squared times x squared minus 5 times x plus 9 quantity is going to get multiplied to c times x plus d over x squared minus 5x plus 9, but the trinomial is going to cancel for both of them. And so I think it's going to look like this. So there are little bits of the denominator that appear in each term of the right hand side of the equation. And they're just pieces, like they're not in the pieces of the denominator aren't in its original form. So for an example, right, like you saw that we multiplied b over x by x squared times x squared minus 5x plus 9 quantity, and we just got rid of a factor of x, and then we got b times x times x squared minus 5x plus 9 quantity. So we can try to be clever. We can try to be clever and we'll try to substitute a value of x into that equation. Um, but to do that, we have to know like what's the value of x. If we set x to something and then plug it back in, what's the value of x that's going to um, decimate the majority of this equation? In this case, here, which this is way one, we've assigned it a name already from before. Let's set x equal to 0 and see what happens. On the left side of the equation, if we set x equal to 0, the left-hand side, this is going to 0, that's going to 0, and we're going to be left with 18 on the left-hand side of the equation. On the right-hand side of the equation, let's see, 0, 0, 8 times 9 plus 0 times 0 times 0, 0 times 9, 0, plus this is going to be 0. This is going to destroy all of those. Okay, so it's literally just going to be 18 equals a times 9. Um, so with a bit of algebraic manipulation, if we divide both sides by 9, a equals 2. But we still need to find 3 more constants. So, you know, we'd better equate coefficients of 3 different powers of x. Let's start off by expanding the equation. So let's start off by expanding the above equation and then grouping together the different powers of x. I mean, look, we need the room. All right, we just need the room. 2 equals a, that can go over here. So the first thing that we need to do is we need to expand all of these values, and then we're going to group them together. So let's just go rapid fire. I mean, we're going to have 8 times x squared minus 19 times x plus 18 equals a times x squared minus 5 times ax plus 9a. And then over here we're going to have, well, this is going to be, I think this is going to be b times x raised to the third power minus 5 times b times x raised to the second plus 9b times x, and then you gotta multiply that. Okay, so this is gonna be plus c x raised to the third plus dx squared. And let me just check my work. Yep, I think that's good. But then now we want to start grouping them together while paying attention to the different powers of x. So we could put it in descending form. So we have a few different terms that are raised to the power of x raised to the third power, and namely b times x raised to the third and c times x raised to the third. So if we do like b plus c, make it parenthetical, and then just stick x raised to the third on the outside, I think that should be good. And then next up we're gonna do like a raised to the second, a times x raised to the second. Um, we got x raised to the second over here and an x raised to the second over here. So we'll do plus, what is this? I want to pay attention to signs here. A minus 5b. So we got 1, 2, 3 plus d times x raised to the second. I'm pretty sure. And then we got to do b, just like the x's that aren't raised to any power. So it's going to be negative 5a times x, 9 times b times x. And I'm pretty sure that's it. So this is going to be like negative, does that negative go on the outside? Let's just leave it on the inside. Negative 5, negative 5, a plus 9b with an x on the outside. And then we're gonna do our constants. And it looks like there's only one constant, so plus 9a. We're gonna get a system of equations. So what do we need? Like x raised to the third terms, x raised to the second terms, x raised to the first terms, and constant terms. Wow, this is a big matrix. I mean, I know technically I'm not writing out a matrix, but I'm thinking about this in terms of matrices. There's gonna be 0a plus b plus c plus d. My bad, guys. I'm writing on half a brain cell. 0d. So 0a plus b plus c plus 0d equals 0. And then for the second degree, it looks like there's gonna be 1a minus 5b plus 0c plus d equals what? Where's the second? I think there's like 8. Yeah, 8. And then as for x, so we're gonna look at right here. It's gonna be negative 5a plus 9b plus 0c plus 0d. And then x, there's negative 19. And as for the constants, well, there's just 9a plus 0b plus 0c plus 0d equals 18. So then if we wanted to write this as a matrix, this is a 4 by 5. 4 by 5 matrix. 0, 1, 1, 0, 0. And then it's going to go 1, negative 5, 0, 1, 8. Then it's going to go 5, 9, 0, 0, negative 19, 9, 0, 0, 0, 18. And so that's how you'd write this as a 4 by 5 matrix. Um, but how do you actually solve this? Well, that's a good question. I'm trying to think. I'm trying to think. I'm trying to stall by writing it as a matrix. Let's see. Oh, and then the answer came to me. Okay, I know how to solve this. But the only question is, do I move this matrix? I don't know. It kind of looks cool, guys. I can't be the only one who thinks that this is aesthetically pleasing. Let's put it up there. All right. So look, here's what I think. Pretend we don't know that 2 is a, and we're just trying to solve the system of equations. All right. You got 9a equals 18. Okay. Well, then instantly we know that a equals 2. We got negative 5a, but we know that a is 2. So negative 5a times 2 plus 9b plus 0c. So plus 0 plus 0 plus 0. Because there's 0c, there's 0d. It's going to equal negative 19. We could simplify this further. This is going to be what? Negative 5 times 2 is going to be negative 10 plus 9b equals negative 19. Okay, but then if I subtract 10, or no, excuse me, if I add 10 to both sides, then it's going to be 9b. It's going to be 9b equals negative 9. But then if I divide by 9 and I divide by 9, well, that's going to reveal to us that b equals negative 1. B is negative 1. So this really here, so if I move this to the other side, then that would actually mean that B equals negative C. But if B is negative 1, then that means that C is positive 1. Because if B is negative 1, if B is negative 1 equals negative 1, then that means that C is positive 1, right? I'm pretty sure. Because B equals negative C, and B is negative 1, so that makes C positive 1. Then we can solve for D. So we have B, we have A, we have C. So the last thing to do is to plug in for this last equation. A equals well, A equals 2. A equals 2 minus 5 times B, which is negative 1, plus 0c plus d, which we don't know what that is yet, equals 8. And then, let's see, this is going to turn into 2 plus 5, I think. 2 plus 5, plus d equals 8, equals, well, maybe not equal, let's do an arrow. Equals 5, is going to be 7 plus d equals 8, and that means that d equals 1. All right. So a equals 2, b equals negative 1, c, yeah, a equals 2, b equals negative 1, c equals 1, and d equals 1. So that means that we get rid of this a. Oops. Get rid of this a. Well, maybe here, let's write it in. So a is 2, so we'll have a 2 right here. Okay. And then instead of b, well, we know that b is negative 1. B is negative 1, so we're going to have negative 1 right here. And then C is 1. So just put a 1 right there, 1x, or we could just put x, but you know what, we're going to put a 1. And then D is 1, I'm pretty sure. All right. Now, what I shall do is get a new page. So I'm going to go from here to here. I just grabbed this, and I'm moving it over here. All right. We have 8 times x squared minus 19 times x plus 18 over x squared times x squared minus 5x plus 9 quantity. and this equals 2 over x squared plus negative 1 over x plus 1 over x squared minus 5x plus 9. So we're interested in the integral. So we're going to stick this is the integrand. So we're going to have the indefinite integral of 8x squared minus 19x plus 18 over x squared times x squared minus 5x plus 9 quantity integration with respect to x. Of course, this means that we can make all of these integrals within their own right. So we're going to have the indefinite integral of 2 over x squared in integration with respect to x minus, I'm factoring out that negative sign, the indefinite integral of 1 over x integration with respect to x plus the indefinite integral of x plus 1 over x squared minus 5 times x plus 9 integration with respect to x. So now, instead of that giant integral that we had at the beginning, we have 3 much more simpler integrals. And we can even make them simpler. We can make them simpler because look, I can take this 2 and I can factor it. I can factor the 2 out of the first integral. And now we have 1 over x squared integration with respect to x minus 1 over x integration with respect to x plus the indefinite integral of x plus 1 over x squared minus 5x plus 9 integration with respect to x. I think we could take care of the first integral. So let's do this in this nice blue color. So I'm going to look at this one first. We're going to have 2 times the integral of x raised to the negative second power integration with respect to x. Well, that's going to be 2 times x raised to the negative second plus 1 over negative 2 plus 1 plus c, technically, equals negative 2 times 1 over x plus c, technically, which is going to be, that's going to be negative 2 over x plus c. All right. The second one, that's just going to be a natural log, right? Because it would seem that negative 1 times the indefinite integral of 1 over x integration with respect to x is going to equal the negative natural logarithm of x plus c. Then if you combine these two, I think we're going to have negative 2 over x minus the natural logarithm of the absolute value of x plus c. And I would imagine those are the answer. That's the answer for the first two integrals. So that's not really a lot. Um, but um, that would be step 5, integrating the terms with the linear powers on the bottom. Integrating terms with the linear powers on the bottom, right? And we just did that. But then step 6, the final step, would be to integrate the terms with the quadratic on the bottom. And that's what we're going to be looking at right over here. This is let's see, x plus 1 over x squared minus 5 times x plus 9 integration with respect to x. And yeah, I mean, we're going to have to complete the square. Let's see. X squared minus 5x plus 9. The first thing to do is to just like focus on the x terms. So mainly we're looking at x squared minus 5x. Wow, okay. So we need to take that 5x, the negative 5x, negative 5 divided by 2, negative 5 divided by 2 raised to the second power. Negative 5 times negative 5 is 25. 2 times 2 is 4. Okay. And instead of putting 6.25, we'll just leave it as a fraction. So then the next step would be to insert this inside of what we have in a specific way. So we have x squared minus 5x. Then we have to plus and minus it. So plus, so what, 25 over 4 plus that 9 minus 25 over 4. Okay. It's a minus b quantity squared. A squared minus 2 times a times b plus b squared. Now here, this will still be the same, but here a is going to be x, and b is going to be 5 over 2. That's going to be, the square is going to be x, I'll put an arrow, x minus 5 halves squared, right? And then that's going to account for these guys here. So we'll have plus 9 minus 25 over 2. Excuse me, 25 over 4. Okay, this is going to be, yeah, x minus 5 halves quantity squared plus 9 minus 25 over 4. Of course, we could simplify this to x minus 5 halves quantity squared plus 9 times 4 is 36. 36 over 4 minus 25 over 4. That's going to be x minus 5 halves squared plus 11 over 4. 11 over 4. That means that the integral here Let's just rewrite it. I'm going to do the denominator first. Numerator is x plus 1. Integration with respect to x. And so, yeah, and so this is actually going to be the indefinite integral of, uh, well, the numerator is going to be x plus 1 still. And then we're going to grab our new denominator with a sign change right here. X minus 5 halves squared plus 11 raised to the fourth integration with respect to x. And then this is we're gonna have to do some substitution. Um, so we'll do some substitution here. And if we let u equal x minus 5 halves, we can solve for x. Now x equals u plus 5 halves. And of course, the derivative of u is just going to be 1, so it's just going to be dx. We can go through with our substitution. I don't know if we have enough room here. Let's make room. So now we'll just go and we'll apply our substitution. It's going to be, well, we know that x is equal to u plus 5 halves. And that's going to be plus 1 right there. And then, well, in the denominator, we're just going to have u squared plus 11 over 4. And this is going to be integration with respect to u now. And well, at this point, we could just split up the integral. No, we can't, not yet. First, we're going to combine some like terms. We're going to drop these parentheses here, and we're going to have the indefinite integral of u plus 5 over 2 plus 2 over 2. In the numerator, we get that u squared in the denominator plus 11 over 4. Integration with respect to u. This is going to become the integral of u plus 7 over 2. In the denominator, we're going to have u squared plus 11 over 4. Integration with respect to u. And then at this point, we can split the integral. So let's let the first integral be u over u squared plus 11 over 4 integration with respect to u, and then plus the indefinite integral of 7 halves over u squared plus 11 over 4. But I'm just going to hop on factoring that 7 over 2 out. Just to take it out because then we're going to have inside of the integrand 1 over u squared plus 11 over 4. And then integration with respect to u, right? So now we do need some more room. Okay, and so at this point, I have everything like underlined so we can see like what's what. We have these completed integrals here with the answer here, and it's underlined in the same color. And then right now we're working on this larger integral, this third integral, which is broken up into two separate ones, and we're going to work on evaluating this one underlined in a darker blue first. Now, for this integral, for this integral, um, we so for this integral, like if we wanted to do u substitution, and we're just gonna do this like in our head really quickly. So we have the indefinite integral of u over we have the indefinite integral of u over u squared plus 11 over 4 integration with respect to, oops, oh my gosh, my bad guys. I just realized this is all supposed to be integration with respect to u at this point in time. Integration with respect to u, integration with respect to u, integration with respect to u. But if we took the derivative of the denominator, right? Like let's say we wanted to do like substitution, and we set the substitution variable to u squared plus 11 over 4. Well, the derivative of u squared is 2u, and the derivative of 11 over 4 is 0. So we're going to have the derivative being 2u. And in the numerator, we don't have 2u, we have u, which is technically a constant multiple, or I guess it's a multiple of it, but it's just a partial multiple of it. So to fix this, what we can do is um, we can actually multiply the top and the bottom um, of the integral. So we can multiply the top of the, or we can multiply by 2 and divide by 2 simultaneously. And apply that. So we have u over u squared plus, excuse me, yeah, wait, oops, u squared plus 11 over 4. Integration with respect to u. Um, and what? Well, and then we'll factor out that 2 in the denominator, and we'll have 2u up top, and then in the denominator we're gonna have let's see, u squared plus 11 over 4 integration with respect to u. And and so now we're getting somewhere because now we can do some u substitution, or so we could do some substitution. We have to pick a different variable, not u. Um, and so I choose psi, or psi as my grandmother calls it. So, but psi, Poseidon, it's a trident. Let's set psi, right, equal to let's set it equal to um u squared plus 11 over 4. That means that the derivative of psi is going to be 2u, which we have in our integral. So, oh yeah, uh, uh, 2u du, which we have in our integral. So now we're going to do 1/2 times the indefinite integral of 1 over psi, integration with respect to psi. So that's going to be 1/2 times the natural logarithm of the absolute value of psi, plus c. And then we'll have to back substitute. So we're going to have 1/2 times the natural logarithm of u squared plus 11 over 4. But at this point, we could drop the absolute value brackets because it can only ever be positive. Um, but at the same time, we're also going to back substitute for u. So we have 1/2 times the natural logarithm of what we set u to back here. So we set u equal to x minus 5 halves. So we're going to have um, x minus 5 halves. But remember, we squared it. Um, let's see, plus 11 over 4 plus c. All right. So I'm at this point, like, I'm not, uh, I'm not gonna multiply out this last expression. I'm just gonna look at the equation. I'm not gonna bother multiplying this out because we could multiply this out. And I'm talking about like what's in this absolute value brackets here. Um, but do you remember earlier, this is what we used to complete the square. X minus 5 halves quantity squared plus 11 over 4. See, this is what we had gotten originally from this expression here. So I can just take this and I can just put it back into this form. I do believe that I can. So that's what I'm going to do. We're going to have um, 1/2 times the natural logarithm of what we had before we completed the square. Um, we don't have to do the absolute value brackets because it's only ever going to be positive. So we'll have the 1/2 times the natural logarithm of x squared minus 5x plus 9 plus c. So this one's solved, and now we have one more left. This one. And so we'll get started with that right here. 7/2 of the indefinite integral of 1 over, we got u squared plus 11 over 4 integration with respect to u. Um, okay, yeah, so for this one, there's a formula to be applied. It's the arctangent formula from before. So let's let a equal the square root of 11 over 4, which is equal to, well, you can't take the square root of 11. So we'll leave that like that. You can take the square root of 2. So you got 11, the square root of 11 over 2. Having applied this, well, we should get something that should look like this. We got a 7 over 2 times the indefinite integral of plus 11 over 4 integration with respect to u, but that's equals 7 over 2 times what? Well, a is, this is going to be like 1 over, this is a complex fraction, this is going to be 1 over 11 over 2. But then if we reciprocate it, that 2 is going to come out top. But we'll get to that in a second. Just want to get this down, just try to think this through. Arctangent of, we got x over a. So we have u over the square root of 11 over 2. And then plus c. And then, well, this is going to turn into 7 over 2 times the reciprocal 2 over the square root of 11. Um, well, this is going to just become, well, 14. These twos are going to cancel. So it actually 7 over the square root of 11. Um, arctangent of huh, of 2u, because we're going to reciprocate 2u over the square root of 11 plus c. Um, but then we want to back substitute for u, because u is set to x minus 5 over 2. Hold on. 7 over the square root of 11 times the tangent, inverse tangent of, gosh, 2 times um x minus 5 over 2 over the square root of 11. Okay. And so what is this going to turn into? Uh, well, I think it's like, I'm not sure this is right, you guys. 7 over the square root of 11 arctangent um of, let's see, 2x minus 5, because this is going to turn into 10. This is going to, well, 10 divided by 2 is 5, so minus 5 over the square root of 11 plus c. To put this all together, this is going to be the indefinite integral of x plus 1 over x raised to the second power minus 5 times x plus 9 integration with respect to x. And then we could just put this all together, guys. We're gonna put this all together. Okay, the square, so this is gonna be equal to 1/2 times the natural logarithm of x squared minus 5x plus 9 plus 7 over the square root of 11 times arctangent times arctangent of 2x minus 5 over the square root of 11 plus c. So the first integrals that we got the answers to was 1/2 x squared minus 2x. So this here in blue. Then, let's see, we did a partial fraction decomposition with this integral here with the quartic. And then that's what all this is. And then we kept working on it. Kept working on it. And then we got these answers here for these two integrals because it got split into 3 other integrals. And so we got the first 2 integrals. So that's what's going to be underlined here in this light blue. And then we found this for that third integral right here, underlined in pink. So let me see this. I don't know what color we settled on, but this is the answer for that. So let me be very clear. We'll use orange. For this entire integral, we split off two more integrals, and we found this here to be the answer, the combination of both of those two integrals that we split off. This quartic integral here required partial fraction decomposition, which is what we worked on um, through this portion. Then we brought it over here. We kept breaking it down. We found its form. Um, we did the system of equations. We found the values. We were able to set it up. We broke what we set up back into three separate integrals, and then we found the answers to these two integrals here and here. Um, we brought them with us. We brought them with us. Let me use orange again. Because those answers were right here, right? Those answers were right here. And then we found another answer, so because we had split off those two separate integrals, then we found another answer to the last one, which is the largest one. So in conclusion, the indefinite integral of x raised to the fifth minus 7 times x raised to the fourth plus 19 times x raised to the third minus 10 times x raised to the second minus 19 times x plus 18 over x raised to the fourth power minus 5 times x raised to the third power plus 9 times x raised to the second power with integration with respect to x. Well, that's equal to the indefinite integral of x minus 2 plus 2 over x squared minus 1 over x plus 1 over x squared minus 5 times x plus 9 integration with respect to x. In other words, this is equal to 5 different integrals that we just worked out. And the final answer, 1/2 x squared minus 2x minus 2 over x minus the natural logarithm of the absolute value of x plus 1/2 times the natural logarithm of x squared minus 5x plus 9 quantity plus 7 over the square root of 11 times arctangent of 2x plus 5 over the square root of 11 plus the arbitrary constant. And that's our answer. The last problem that we worked through was more chosen to exemplify all 6 of these steps that we came up with when working with a rational function in an integrand, so the integral of a rational function. But more realistically, we'll be given a problem that looks like this in a Calculus 2 class, in your standard Calculus 2 class, when you're prompted to use partial fraction decomposition to solve for an integral. So I wanted to finish off this video here with 3 integrals that are of these 3 forms. So I want to finish off the video with 3 more integrals that are more reasonable. So let's evaluate the indefinite integral of 4 times x minus 2 over x cubed minus x, integration with respect to x. Well, if we look at our game plan here, we can check the degrees, and the degrees on the bottom are indeed bigger than the degrees on the top. So the next step would be to factor the denominator. So we'll go ahead with the factorization of this denominator here. And well, I could see that I'm able to pull out an x. And so I went ahead and I pulled out an x there, and then well, this x here, this x minus 1, this is the difference of squares, so we can factor it further, and it will look like this. And well, when we look at these, we can see that, well, these are all unique linear factors. So that's going to be number 2, the unique linear factors. Because these are unique linear factors, we can set up our partial fraction decomposition as follows. Now this is going to be case one. If you have a linear factor like x plus a, then the form has a term like a over x plus a, capital A over x plus a. In this case, um, for x, well, the 0 is going to serve as the a. So we're going to have a, well, x plus 0 is just x, right? Then for b, we got x plus a. This is going to be x plus 1. And then for c, this is going to be x minus 1. Okay, so at this point, what we have to do is we have to multiply both sides by the least common denominator. So I'm just going to throw this in parentheses. And I'm going to just multiply both sides by the LCD. Well, this is going to cancel with this, and we're going to have 4x minus 2. And then let's see over here. Well, that x is going to cancel with this x here. We're going to have a times x plus 1 times x minus 1. Um, plus b, and then b, the second term here, it's going to interact with the LCD in such a way where the x plus 1, it's going to cancel with the x plus 1 in the denominator, and it's going to be, well, b times x minus 1. And then for the c, well, these are going to cancel each other out, and we're going to end up with plus c times x over, or excuse me, c times x plus 1. Let's try to solve this by guessing at the different values for x. How can we do this? Well, let's bring our attention to the LCD. The LCD can be 3 different things. So I'm pretty sure that the LCD can be, well, if you set this all to 0, you're going to have x equals 0 for one of them, namely this one. For x plus 1, well, if you set x plus 1 equal to 0, well, that's just going to mean that x is equal to negative 1. Then, well, if you have like x minus 1 equals 0, then that means that x equals 1. What happens to the equation when x equals 0? Well, then we're going to have 4 times 0 minus 2. Oh, that is not trying to go in. Let's go. There you go. 4 times 0 minus 2 equals a times 0 plus 1 times 0 minus 1 plus b times 0. That's like a backward 6. Plus b times 0 times 0 minus 1 plus c times 0 plus 0, times 0 plus 1. C times 0 times 0 plus 1, right? And then, well, what's going to end up happening is we're going to have some cancellation here. We're going to have some cancellation here, right? Because b times 0 times negative 1 is just going to be 0. C times 0 times 1 is just going to be 0. So then what we have over here on this side is going to be negative 2 equals negative a. And if you multiply both sides by negative 1, that's going to reveal that a equals 2. Okay? So what about for the next case? What about for the case where x equals negative 1? Well, in the case where x equals negative 1, that's going to be 4 times -1 minus 2 equals 8 times -1 plus 1 times -1 minus 1 plus b times -1 times -1 minus 1 plus c times -1 times -1 plus 1. And then what's going to end up happening here? Well, it looks like in this case, the A term is going to get canceled out, and the C term is going to get canceled out. That's going to be -6 equals 2 times B, and then well, that's going to reveal to us that B equals -3, I think. And then let's check out the third case where x equals just 1. So in the case where x equals 1, we're just going to plug in 1 everywhere where we see an x. So it's going to be 4 times 1 minus 2 equals a times 1 plus 1 times 1 minus 1 plus b times 1 times 1 minus 1 plus c times 1 times 1 plus 1. Well, in this case, it looks like a is going to cancel, and then it looks like also the b is going to cancel, and that's going to leave us with a c. So let's try to see what's going on with the c term. Well, 4 minus 2 is going to be 2. So 2 equals 2c, and that's just going to mean that c equals 1. Okay, so well, now at this point, it's like we need to set it back up. So we know what a is, we know what b is, we know what c is. So we're just gonna go through. We're just gonna go through with this. 2 over x minus 3 over x plus 1 plus 1 over x minus 1. This is going to give us 3 separate integrals, and I'm just going to go ahead and factor out that 2 of the first one immediately. 2 times the indefinite integral of 1 over x integration with respect to x. Factor out that 3 immediately. And this is going to be minus 3 times the indefinite integral of 1 over x plus 1 integration with respect to x. And then this is going to be plus the indefinite integral of 1 over x minus 1 integration with respect to x. Now, there's a formula that we have to keep in mind for these two, 1 and 2 specifically, as well as this one, but I think we've already written it down in this video before. But you know what? I'll write it down. So for this one here, the formula is going to be like the integral of 1 over x integration with respect to x is going to equal the natural logarithm of the absolute value of x plus c. And then for these two, 1 and 2 here, alright, so that's going to be the indefinite integral of 1 over x plus k integration with respect to x equals the natural logarithm of the absolute value of x plus k plus the arbitrary constant. So let's go ahead and apply that. So having applied both of these formulas, it's going to leave us with 2 times the natural logarithm of the absolute value of x minus 3 times the natural logarithm of the absolute value of x plus 1 plus the natural logarithm of x minus 1 plus c. Now, there is a specific rule, a logarithm rule that we can apply to this expression here, and I'll write it out. So this says that the natural logarithm of a value raised to the power of n equals n times the natural logarithm of that value. So the natural logarithm of a raised to the power of n equals n times the natural logarithm of a. So we're basically bringing those coefficients out front. Just one thing to note here is that the third expression, the natural logarithm of x minus 1, that doesn't have a coefficient, so we're just going to leave this one the same, and we're going to apply it to these two here. So the expression becomes the natural logarithm of the absolute value of x raised to the second power plus the natural logarithm of the absolute value of x minus 1 quantity, all minus the natural logarithm of the absolute value of x plus 1 raised to the third power plus c. So now at this point, we're going to apply the product rule of logarithms to our expression here. So this just says that the natural logarithm of the absolute value of a plus the natural logarithm of the absolute value of b equals the natural logarithm of the absolute value of a times b. So both of them just go inside of those absolute value brackets. So let's go ahead and apply this. And I'm just showing the application of the terms in the expression that are going to have that are going to be using this. And so now we're going to put this all together. So this is what the expression will look like. It's the natural logarithm of the absolute value of x raised to the second power of x minus 1 minus the natural logarithm of the absolute value of x plus 1 raised to the third power plus c. Now, at this point, there's one last rule that we can apply, and it's a logarithm rule. This says that the natural logarithm of a minus the natural logarithm of b is the same thing as the natural logarithm of the rational expression a over b. So let's go ahead and apply this rule. And it turns out this is actually going to be our final answer. So this is the natural logarithm of x squared times x minus 1 quantity over x plus 1 quantity raised to the third power plus c. And this is going to be our answer for this problem here. Okay, let's do another one. We got the indefinite integral of 4 times x minus 2 over x cubed plus x integration with respect to x. The first thing to do here, because the degree is higher on the bottom than it is the top, we're good. That checks out. So we just have to factor the denominator. I'm going to leave the numerator the same. I'm going to go in on that denominator. I'm going to take out an x. Okay, so now we can see that the denominator here, this is a quadratic irreducible. Okay, so since this is a quadratic irreducible, we're going to need to do some partial fraction decomposition. So we're going to go ahead with the partial fraction decomposition because this is a quadratic irreducible. So I'm just going to rewrite this out. So this is what the partial fraction decomposition form is going to look like. We got a over x plus b times x plus c. And we know this because of our forms here. Where are we at? Right here at number 3 for our quadratic irreducible. And so in the denominator, we're just going to have x squared plus 1. Now what I'm going to do is I'm going to multiply this entire expression by the LCD. Same way as we did before. So we're going to do multiply this entire thing by x times x squared plus 1 quantity. And then As you can imagine, there's going to be quite a bit of cancellations. Now, this denominator is going to go away on this side, on the left-hand side of the equation. So we're going to have 4x minus 2 equals, well, these x's are going to cancel right here. So we're going to have a times x squared plus 1. And then the x squared plus 1, the x squared plus 1 over here are going to cancel. And it's, well, we're going to have plus b times x plus c times x. So now hold on, I'm trying to think about what we have to do here. Um, I think the move at this point is to probably just try to multiply everything out and then regroup it as needed. So that's going to be like a times x squared plus a. This is going to be plus bx squared plus cx. So now let's try to regroup everything together. Um, so let me just like rewrite this. This is going to be 4 times x minus 2 equals a plus b both times x squared plus c times x plus a. Now I'm just gonna set up like a systems of equations x squared. So all the terms that have x squared in it, it's gonna be right here. So we're gonna do a plus b, and then I'm gonna leave a space here because there could be a 0 here. So, or well, there could be a c here because there's a c in this expression. This is just the way my professor showed me how to do it. Shout out Professor Michael Farquhar for showing me how to do this. But it's like equals 0. Then I'm gonna do the x terms. So we're gonna do blank, blank, but there is a c and an x. 0a plus 0b plus, that was an 8. 0b plus, well, there's one c, there's one constant of a, there's 0 b's, and there's 0 c's, and that equals -2. So we have a system of equations here. Um, okay, well, let's see. If there's 0 c's, that means that we know that a equals a -b, and c equals 4. C equals 4, and a equals -2. I'm like confused though. No, I'm not. If a equals -2, that means that b equals 2, +2. And so, well, that means that we can rewrite our integral. Oops. That means that we could rewrite our integral. And I might as well rewrite it over here, right? So the integral, we're gonna plug in for a. So we got the indefinite integral of -2 over x plus, now we have to plug in for b and c. So that's gonna be 2x plus 4 over x squared plus 1, integration with respect to x. Um, and so then what we can do is we could factor out the -2. That does not even look like an equal sign. Hold on. We can factor out that -2. 1 over x integration with respect to x, and we're just splitting up the integral here. We could split up this here, this in the integral. We could split this up into two separate integrals like this. So this is going to be plus 2x over x squared plus 1 integration with respect to x. And then this is going to also, so this is going to be plus 4 over x squared plus 1 integration with respect to x. Okay, so I look at this one and I'm like, okay, this is gonna be like a natural logarithm, -2 natural logarithm of the absolute value of x. Like we already know that. But for this one, I think this one is a u substitution because if I took the derivative of the denominator, that's gonna be 2x, and that's in the numerator. Um, so in other words, let me see, I'll do a different color, get some variety here. In other words, we know what's gonna happen with this one. With this one, but this is gonna involve u substitution. So let's let let's let u equal x squared plus 1, and its derivative we know is just going to be 2x dx. Um, so we can rewrite this. We can rewrite this as -2. I mean, well, we already know it's the natural logarithm, so -2 times the natural logarithm of the absolute value of x. Then let's do our substitution really quickly, and I'll stick with the same color because this is going to be plus, this is going to be plus, say, u over u integration with respect to x, which that's just going to be another natural, integration with respect to u, I meant. But that's just going to be another natural logarithm situation, I'm pretty sure. Uh, and then for this one here, let's factor out that 4. And then now it's going to be like 1 over x squared plus 1 integration with respect to x. But the thing about this one is like, is a formula that can be applied. And I'm going to write the formula up top, like up here. Okay, so now we're going to have some transformations that are going to take place. So let me write them out, and I'll write them out over here. This is -2 times the natural logarithm of x plus the natural logarithm of u, and then we're going to have plus 4 times the arctangent of x plus c. But then the thing about this here is like we have to back substitute, of course. We have to back substitute. So that's back substitute. So now we'll have -2 times the natural logarithm of x plus the natural logarithm of what we set u to, which is x squared plus 1, plus 4 times arctangent of x plus c. Of course, we could rewrite this so it will make the next rule seem a little bit clearer, in my opinion. So I'm gonna take this positive. I'm gonna take the second term because it's positive, and I'm gonna put it up front because I want to show you guys something. So we have the natural logarithm of the absolute value of x squared plus 1 minus 2 times the natural logarithm of x plus 4 times arctangent of x plus c. And then so there's a rule here. There's a logarithm rule here, the one that we went over earlier, but it's the one that goes like this. And so basically this says that if you have the natural logarithm of the absolute value of a minus the natural logarithm of the absolute value of b, that's the same thing as the natural logarithm of the absolute value of a over b. So we can go ahead and we can apply this to what we have. And to be clear, well, in this case, here is going to be a, and then here is going to be b. I don't know, it makes it easier for me to sort of understand what's going on. And so, well, this is all going to equal, having applied that rule, this is going to equal the natural logarithm of, and because keep in mind that we could drop these absolute value brackets because x squared plus 1 is only ever going to be able to be positive. So I'm just going to throw this in parentheses. It's the natural logarithm of x squared plus 1 over x squared plus 4 times arctangent of x plus c. And I'm just going to check my work really quickly. And so, yeah, this is going to be our answer. All right, I got one more problem for you guys. This one is the indefinite integral of 4x plus 2 over x times x plus 1 quantity squared integration with respect to x. So I'm just going to take a look at this here, and then I'm going to recognize that the degree on the bottom is higher than the degree on the top. So that checks out. Let's see here. So let me get this set up. So for the factor of x in the denominator, it's going to be number 1. And uh, it's going to be capital A over x plus a, such that a is equal to 0. So we're literally just going to have a over x. Now, as for the factor of x plus 1 squared, well, for this one, we're going to use rule 2. The term x plus 1 quantity square is a square of a linear factor. And so we're going to honor this form. We're going to honor this form right here. So this is what the setup should look like. A over x plus b over x plus 1 plus c over x plus 1 squared. And so, well, at this point, what I'm going to do is I'm going to multiply both sides by the LCD like we did before. So on the left-hand side, we're going to get 4 times x plus 2. On the right-hand side of the equation, well, this x is going to cancel with this x. It looks like we're going to have a times x plus 1 squared. Now, for this term here, for the b term, for the second term on the right-hand side of the equation, only one of the x plus 1s are going to cancel. So, So we should have b times x plus 1. And then, well, for x plus 1 quantity squared and x plus 1 quantity squared, those are both going to cancel. And then we're just going to have the multiplication of the c just to x. And so yeah, so that's what that's going to look like. For this a term here, a times x plus 1 quantity squared, we can, well, we can, this is a square, so so we can apply this formula here, and I'll write it off to the side over here. Actually, no, I'll write it up here in pink. We can write that out as a times x squared plus 2 times x plus 1 plus b times x squared plus x. Right? Just distributed this x to here, but we left the b on the outside of the parentheses, plus cx. And then, let me see here. That's not the color we used. Where's the color we used? Is it this one? Something like that. Um, so that's that. And let's go ahead and multiply these out then. So we got 4x plus 2 equals a times x squared plus 2ax plus a. And then we'll do plus bx squared plus bx plus cx. And then from here, we could set up our system of equations. So the highest degree that we have, it's x squared. And then we'll go down to x raised to the first, and then our constants. And that's going to be, so we have x squared, so we're going to have a plus b plus 0c equals 0, because on the left hand side of the equation there's no x squared term. But then for just x, we're going to have 2a plus b plus c equals 4, because on the left hand side of the equation there's an x attached to that 4 there. And then for the constants, well, it's going to be a plus 0b plus 0c equals 2. And so that's going to be our system of equations. And so let me just stare at this and try to figure out what's going on. Oh, well, there's one that's given to us. A equals 2. So also over here, looks like a equals negative b, therefore negative b. Well, here, let me try to separate that. Negative, oh, excuse me, not negative b, just b equals negative 2. Then from here, we're going to solve for c. So we're going to have 2 times a, and we know that a is 2, plus b, but we know b is negative 2, plus c. We don't know what c is, but we know that all of this is equal to 4. So, that said, we got 4 minus 2, so we're going to have 2 plus c equals 4. If you subtract that from both sides, we're going to get c equals 2. And then, yeah, and I'm going to throw this in some parentheses. And so we have our setup. So the indefinite integral, so we have a over x. Well, we know that a equals 2. So we're going to have the indefinite integral of 2 over x minus b, and we know that b is negative 2, right? So it's going to be minus 2 over x plus 1. And then c is 2, and so we'll plug that c back in up here, and that's going to be plus 2 over x plus 1 quantity squared, integration with respect to x. And then I'm gonna factor out that 2 from this first integral here. But bear in mind that this is 3 separate integrals. So this is gonna be 2 over 1, 2 times the indefinite integral of 1 over x integration with respect to x minus 2. I'm gonna factor out that 2. Then we're gonna have 1 over x plus 1 integration with respect to x. And then we're gonna have I'm going to factor out that 2 right here as well. So we're going to have plus 2 times the indefinite integral of 1 over x plus 1 quantity squared, integration with respect to x. I mean, like, I know what's going to happen with these two, but with this one here, it's not as straightforward. So we will do some substitution with this one here. U equals x plus 1, then its derivative is going to be 1 or just dx. And so I'm pretty sure that these are going to go like this. So 2 times the natural logarithm of the absolute value of x plus, what am I talking about? Plus? No. Minus 2 times the natural logarithm of x minus 1. X minus 1. Plus 2 times the integral that we just did the substitution for. So that's going to be 2 times, well, let me just be clear with this guy. So if I did some u substitution, I would have 1 over u squared integration with respect to u, but that's the same thing as u raised to the negative second power, the indefinite integral of u raised to the negative second power integration with respect to u. And so that's what I think I'm going to roll with. So we'll do u raised to the negative second power integration with respect to u, just because that makes it easier for the application of the power rule. So let me grab this here and I will write out the power rule. Having applied the power rule, well, that would mean that we're going to have, that this is going to equal 2 times the natural logarithm of the absolute value of x minus 2 times the natural logarithm of x plus 1. So I'm going to apply the power rule, and this is going to be 2 times what? U raised to the negative second plus 1 over negative 2 plus 1, like that. And so that's going to equal 2 times the natural logarithm of the absolute value of x minus 2 times the natural logarithm of the absolute value of x plus 1 plus 2 times negative u raised to the first power. Okay, but that's the same thing as 1 over u. Okay, then we have to hit it with a back substitution. So we're going to have, well, 2 times the natural logarithm of the absolute value of x minus 2 times the natural logarithm of the absolute value of x plus 1 plus, well, we'll back substitute for u, which was just x plus 1 in the denominator, but then we're going to multiply that to that 1. Oh, but this is a negative. This is minus, so it's a minus. Yeah, so this is going to be minus. And then minus 2, because that 2 is going to get multiplied to that negative 1. So it'll be negative 2 over x plus 1 plus c. And so this is going to be our answer here. That is 2 times the natural logarithm of the absolute value of x minus 2 times the natural logarithm of the absolute value of x plus 1 minus 2 over x plus 1 plus the arbitrary constant. And so yeah, I think that's going to do it for this video. I appreciate you guys for watching, and I hope you have a good day.